Welcome everyone to part 3 of the section 8.2 notes. We're going to do this page a little bit out of order. We're actually going to start with the second item, then jump down to the fourth one, and then the third one, and then go back to the first. Maybe I should reorder these in the future, but it's too late for that now. So, okay, so let's start with the second item here. Let's just determine if this infinite series converges or diverges. Well, this does not look anything like, remember, it has to look like, if we're starting with n equals 1, then it has to look like a times r to the n minus 1. So let's see if we can get it to look like that. Okay, well, this here, that's the sum n equals 1 to infinity. You'll notice that this is actually 4 to the n, because it's 2 squared to the n. And now this one is times 3 to the 1 minus n. Well, I'm going to write that as 4 to the n times 3 to the negative n minus 1. I think that works, right? If I distribute this negative, I get minus n plus 1, which is exactly 1 minus n, right? And now what I know about negative powers is that they can move to the bottom. So this is actually the sum n equals 1 to infinity, 4 to the n over 3 to the n minus 1. Since I moved it to the bottom, that negative becomes a positive, and so I get something like that, right? This is still not in the form that I need. I have 3 to the n minus 1, but I have an extra factor of 4. So what I'm going to do is I'm going to peel one off. So I get 4 times 4 to the n minus 1 in the numerator, and I still have 3 to the n minus 1 in the denominator. Okay, now I'm in good shape here. This is 4 times 4/3 to the n minus 1. And now you'll notice my r value is 4/3, which is bigger than 1, or bigger than or equal to 1. So this actually diverges, right? Okay, so since 4/3 is bigger than or equal to 1, the geometric series diverges. And we learned that on the last page. Right? Okay, so I like these examples here where you take repeating decimals and turn them into fractions. So what you learned way back when you were young is that rational numbers come in 2 flavors. There are those whose decimals terminate, so think like 1/2. All right, that's just 0.5. The decimal has terminated. There's no more stuff after here, right? Or they end in a sort of a repeating fashion, right? So think of like 1/3. That's 0.3 repeating, right? So the decimals never terminate. This 3 goes on forever and ever, but you never get anything new, right? It's always just, eventually it's just 3s all the way down. So this 0.46 repeating, well, this is a rational number. You probably don't know what it is. Maybe you can guess. But what we're going to use is geometric series to find out exactly what rational number it is. Okay, so that's just a little sidebar there. Let's get into this. What we're going to do is first write this as decimal numbers. So 0.46 repeating is 0.46 plus 0.0046, right? Notice when I add these two together, I don't add anything to the first 2 decimals, right? Then I tack on a 4/6, then I get and then 4 zeros and then a 4/6, then 0.6 zeros, and then a 4/6. And so what this is doing is every time I'm just adding on a 0.46 in the next 2 decimal places, right? And keeping everything else the same by only putting zeros there. Okay. Well, this is, let's see here. 0.46 is just 46 over 100, which I'm going to write as 10 squared. So 46 over 10 squared. I hope you'll allow that. The next one here, 0.0046, well, that's 46 over 10,000, which I'm going to write as 46 over 10 to the 4th. You guessed it. What do you think the next one is? 46 over 10 to the 6th, probably, yeah? Plus 46 over 10 to the 8th, maybe, and so on. And so we see that this repeating decimal is actually an infinite series. It's the sum n equals 1 to infinity. Let's see if we can somehow find what we're adding up here. Well, we always get 46 on the top what power of 10 do we get on the bottom? Well, when n equals 1, I want 2. When n equals 2, I want 4. When n equals 3, I want 6. When n equals 4, I want 8. That sounds like I'm doubling every single time. So I think the power of 10 is 2n. Well, this is definitely not in the right form. Remember, I need it to look like this, right? I need somehow, since I'm starting with n equals 1 here, I need an n minus 1 for my power. So this is the sum n equals 1 to infinity. Let's just use some rules of exponents. So I get 46 over 100 to the n. 10 to the 2n is 100 to the n. That's still not right. Let's see, what can I do? Well, the first thing I can do is write 1 over 100 to the n as 1 over 100 all to the n. Okay, that's good. We're getting there. We have a number times a common ratio to the n. Well, I need an n minus 1, right? I'm starting with n equals 1, so I have to have n minus 1 here. So how about I just peel off a factor of 1/100th? Okay, now we're in good shape. This is the sum n equals 1 to infinity. 46 over 100. You could reduce that, but I'm actually going to leave it as is for the moment, and you'll see why soon enough. But here we go, right? Notice my r value. That's the only thing that matters when it comes to convergence. A can be whatever, as long as it's fixed, right? 46 over 100 is fixed. R is what determines convergence here. And now, is 1 over 100 less than 1 but bigger than negative 1? Yes, of course, right? So what I get is just a over 1 minus r. 46 over 100, which is my a value, over 1 minus 1/100th, which is my r value. Well, this is 46 over 100 divided by 1 minus 1/100th is 99/100ths. So I get 46 over 100, flip and multiply, 100 over 99. And that's why I left it unsimplified, because these 100s nicely cancel for us. And so that's 46 over 99. Beautiful, right? I encourage you to plug this into a calculator and see that you'll get, if you do 46 divided by 99, you'll get 0.46464646 until you run out of room on your screen. So that's just miraculous to me that you can somehow do that. All right, so let's come up here. You'll notice this one here is actually 2.3 if I wanted to use the bar notation, and then it's 1/7 with a bar over just the 1/7, right? Okay, so here's how we're going to do this. The first thing we're going to do is we're going to find the non-repeating portion, which is the 2.3, and then we'll write it in terms of the repeating portion thereafter. So this is 2.3 plus 0.0 and then 1/7 repeating. Notice the 0 is not repeating. I just need that empty space there where the 3 was. Okay, and so this is 2.3 plus 0.017 plus 0.00017 plus 0.0000017, right? The next one would be 7 zeros, and then a 1/7, and so on and so forth, right? All right, so what we're going to do is we're going to focus just on this portion here, so just the repeating portion, and then we'll come back to the 2.3 at the very, very end. So 0.017 with the 1/7 repeating. I mean, I have it right here, but you'll notice that that is 17 over 10 cubed, I think, plus 17 over 10 to the, what do you think, 5 maybe, right? Plus 17 over 10 to the 7 probably. The next one would be 17 over 10 to the 9, and so on and so forth. Well, that is an infinite series, right? And it looks to be geometric, right? You have the same thing, but now the power is sort of changing with every step. That is a geometric series. So let's start with n equals 1. We always get 17 on the numerator. In the denominator, what's our power of 10? Well, when n is 1, my power has to be 3. When n is 2, my power has to be 5. Then 7. When n is 3. When n is 4, I need 9. I'm not quite doubling. I'm doubling and then adding 1, I think, right? So it's 7. The sum, n equals 1 to infinity, 17 over 10 to the 2n plus 1. Right? When n is 1, I get 3. When n is 2, I get 5. I think it works, okay? Now, this is not the right form, so let's work with this a little bit. This is 17 over 10 to the 2n times 10 to the first. Notice I cannot call this 100 to the 2n plus 1 because I need to separate as 10 to the 2n times 10 to the first. Okay, so that's 17 over 10, and now this is 100 to the n, which I'm going to write as 1/100th all to the n. It's still not right, right? I need an n minus 1, so I'm going to peel off a factor of 1/100th. We've seen that in just the last exercise. Okay, my a value now is 17 over 10 times 1 over 100. That's 17 over 1 with 3 zeros, I think. And then 1 over 100 to the n minus 1. Okay, now this is, well, my r value is again 1/100th, so this converges, and it's a over 1 minus r is the value. So that's, excuse me, I need an extra 0 there. So it's 17 over 1,000 divided by 99 over 100, which is 17 over 1,000 times 100 over 99. 2 of those zeros cancel. So this is 17 over 990. Now you might be thinking we're done, but we're not. We just showed the repeating part, what that's equal to, 17 over 990. We still need to add on the 2.3. So 2.317 with a bar over the 17 is 2.3 plus 17 over 990. Add fractions. This is 23 over 10. And I'm not going to go through all the work, but what you get is you get 1147 divided by 495. And I encourage you to plug this into a calculator and try it out, right? Okay, so the reason we're coming to this one last is we see here we get 2 plus a half plus what turns out to be an eighth, which I write as 1 over 2 cubed. This is 1/32, which I write as 1 over 2 to the 5th. And so what we're going to do is we're going to separate this. First, we're going to find what the sum of starting with the 1/2 is, then 1 over 2 cubed, etc., etc., and then just add 2 to our answer, right? So, well, that's an infinite series. See if you can do it on your own. What is our power of 2 starting with n equals 1? It's 1 over 2 to the, well, when I get n equals 1, I need a 1. So it's tempting to say n, right? But when n equals 2, I'm supposed to get 3, but that's no good. Okay, and I need, when n equals 3, I need 5. Well, all of these numbers are less than one less than a multiple of 2, so perhaps it's 2n minus 1. Hopefully you're able to get that if you tried it on your own. Okay, well, let's see what we get. This is the sum, n equals 1 to infinity, 1 over 2 to the 2n times 2 to the negative 1. A negative power just means move it to the, if it's in the bottom, move it to the top, right? So this is the sum, n equals 1 to infinity. I get a 2 to the first over 4 to the n, right? This is the sum, n equals 1 to infinity of 2 times 1/4 to the n. Notice dividing by 4 to the n is the same as multiplying by 1/4 all to the n. And now I need to peel off an extra factor of 1/4. All right, so this is the sum, n equals 1 to infinity. It looks like 1/2 because you get 2 times 1/4, and then times 1/4 all to the n minus 1. And 1/4 is my common ratio, r, which is less than 1, but bigger than minus 1. So that means I just get a over 1 minus r. which is 1/2 divided by 3/4, which is 1/2 times 4/3, which is 2/3. Now, this is not the final answer, right? I need to add 2. So 2 plus 0.5 plus 0.125, etc. equals 2 plus 2/3, which is 8/3. All right, well, that's it for this video. It's getting a bit long. In the next video, we'll go over page 58 of the notes.